adding and subtracting radical expressions. This video is going to primarily focus on examples, because I think that's going to be the best way to illustrate the concept and kind of get you used to what the expectation would be for various problems. But before we dive into the examples, let's do a quick review on the conceptual idea behind this adding and subtracting, especially with variables. So let's say we have radical x, so square root of x plus square root of x. And we want to figure out, well, would we be able to condense this down? Like, so could I actually execute this sum between these two radical expressions? So as a reminder, when we're adding, especially variables, we're looking to identify, do we have like terms? And like terms, we've discussed before, is these terms need to have the same exact base variable expressions, and those variable expressions have to have the same exponents. And we know how to convert radical expressions over to their rational exponent equivalent. So square root of x is the same thing as x to the 1/2, x to the 1/2. We can see that the base of these, the variable is both x in each scenario, and the exponents are the same, so we would consider these like terms. Now, when we actually execute the sum, we're going to just ask ourselves, well, how many x to the 1/2 do we have in total? So we have 1 over here and 1 over here for a total of 2 x to the 1/2, and we can convert back to our radical form. So we have 2 square root of x. Okay. Now, that's really the general idea, is we're just trying to figure out like terms. So when we jump into these examples, for the first one, we have square root of 20 minus cube root of 16 plus cube root of 250 minus square root of 5. You would look at these initially and say, well, none of these are going to be like terms. Like if we convert them all over to the rational exponent equivalent, 20 to the 1/2, 16 to the 1/3, 250 to the 1/3, minus 5 to the 1/2. We can see that even though a couple of the terms have the same exponents, none of them have that same base value. So you may think, well, there's nothing to do here. But what we want to do is actually simplify each one of these radicals to see if we actually do have some like terms that would be revealed through the simplification process. So we know how to simplify radicals using either prime factorizations or identifying the largest perfect, say, square or cube, depending on what type of radical you're dealing with, that goes into that, and kind of rewriting the number underneath as a product. So I'll do the simplification both ways, because it depends on, it's like really a preference thing. So let's look at the square root of 20. I'll do the prime factorization for that. So when we break down 20, 2 and 10, 2 and 5, so we can see that the square root of 20 is equivalent to 2 squared times 5. And our radical properties tell us that we could break this apart and figure out that this is 2 root 5, right? So we're going to replace that square root of 20 with a 2 root 5. And just doing that, now you're going to be able to see that this 2 root 5 and that square root of 5 at the end, now we just identified some like terms. So let's also simplify cube root of 16. So cube root of 16, I'm going to do a different way. So instead of doing the prime factorization breakdown, in this case, because we have a cube root, we can think, well, what's the largest perfect cube that goes evenly into 16 upon a division process? So that would be 8. So we could rewrite 16 as the product of the largest perfect cube times some integer value, in this case 2. We can split using our radical properties, and we can see that we're going to get 2 cube root of 2. That second method that I just did to simplify cube root of 16 requires you to know like perfect cubes and perfect squares and things like that. So if that's something you're not familiar with, I highly suggest the prime factorization breakdown, which is what I'm going to use for the cube root of 250. So cube root of 250, we're going to break down. The largest perfect cube that does go into 250 would be 125. But knowing this breakdown is often useful for much larger numbers, especially if you have like 4th roots or 5th roots. It can be difficult to identify what's the largest perfect power of 4 or power of 5 that goes into your number. So we're going to do 2 and 125. We can do 5 and 25, and then 5 and 5. We can see that this prime factorization would result in a group of 5s. So we're looking for a group of 3 with a cube root. And that group of 3 is telling us that we can rewrite this as 5 cubed times 2. Or we can think of it as every time we make a grouping, we remove that number once per group. So there's one group of 5, so I'm going to remove a single 5. And what I didn't group in terms of the prime factors, so anytime I break down a number, we don't consider that as a reminder. So that 2 is a prime number that did not get grouped. That needs to go back inside that cube root. So the equivalent is 5 cube root of 2. Square root of 5 cannot be simplified any further. So now upon simplification, we can see that there's actually some like terms that did get revealed. We see we have a square root of 5 over here and a square root of 5 over there. And then we have a cube root of 2 here and a cube root of 2 there. So we can condense this expression down further from what it initially was. So when we're going to combine these square root of 5s, we're asking again, how many square root of 5s do we have in total? Well, we had 2 over here, and we're subtracting 1. So for a total of 1 square root of 5. Now the cube root of 2, cube root of 2, how many do I have in total? Well, we have negative 2 plus 5 for a total of positive 3 cube root of 2. And there's our final answer. So that would be a condensed sum as far as we can take it, given that initial problem. So make sure that you're simplifying each radical individually to help you identify like terms. So let's look at a few more examples. Again, we're going to look, this time we have all cube roots, and you can see that the radicand, or what's underneath that expression, or that radical, I should say, they're all different. So upon initial observation, you're going to say, well, there's no like terms to be had, but let's see what happens when we simplify. So if we have cube root of 81, let's do a breakdown. We'll do 3 and 27, 3 and 9, 3 and 3. So that means we could rewrite cube root of 81 as 3 cubed times 3, which tells us that group of 3s we're going to remove once per group. And we have that 3 left over. This prime number that did not get grouped goes back under the radical. So we have 3 cube root of 3 is the replacement for the cube root of 81. Then we have minus 2. We got to figure out the equivalent for cube root of 72. So 2 and 36, 2 and 18, 2 and 9, 3 and 3. I can see I have a group of 2s, and there's no third 3 to group that last one. So we're going to have 2 cube root. Both 3s need to go back. We multiply, so we're going to get 2 cube root of 9. And then lastly, we're going to get minus. We're going to do cube root of 24. What's the simplification there? I'll use the other method in this case because 24 is a pretty small number. We can rewrite 24 as the product of 8 times 3. 8 being the largest perfect cube that goes into 24 evenly or without a remainder. So then we have cube root of 8 times cube root of 3, which is 2 cube root of 3. Okay. So now, those first 2 radicals had constant coefficients in front of them, so we're going to perform that multiplication. So 4 times 3, we're going to get 12 cube root of 3, minus 4 cube root of 9, minus 2 cube root of 3. So let's look at like terms. We have cube root of 3, cube root of 3. There's no other cube root of 9, so that's going to be a standalone term, nothing to combine that with. We'll just throw that at the end. So how many cube root of 3s do we have in total? Well, 12 minus 2, we have a total of 10. So 10 cube root of 3 minus 4 cube root of 9. That's the most simplified version. We were able to combine 2 of those terms in the initial expression given to us by simplifying, identifying like terms, and then just asking yourself, what's the total amount of that radical or that like term that I have? Okay, next problem. Simplify the radicals. We can see that they're clearly not the same, especially those radicands underneath. We have 45y squared and 20y squared. So although the radicals themselves are the same, the square roots, what's underneath is not. So we're going to take 45y squared, which is going to be the same thing as this, using radical properties. Square root of 49, we can break apart. Largest perfect square that goes into 45 is 9, so 9 times 5. We know the square root of y squared is y, so I'm actually going to throw that out in front. So this whole thing is y, radical 9, radical 5 is equal to 3y square root of 5. Okay? So we're going to replace that at the beginning. So we're going to get 6, and then instead of square root of 45y squared, we're going to replace with 3y square root of 5. We're going to do that same thing with the square root of 20y squared. Again, we're going to split this up into the square root of our constant value and the square root of our variable term. So we're going to have y, because square root of y squared is y, and then square root of 20, we can break apart into 4 times 5, 4 being the largest perfect square that goes into 20. Or again, if you're not comfortable with that, you can do your prime factorization breakdown, and we're ultimately going to get 2y root 5. So we can make that substitution. Now again, this is a problem where the radicals in the initial problem had constant coefficients, so we want to be able to distribute and multiply or take care of that multiplication. So we're going to have 18y radical 5, or root 5, square root of 5, minus 8y square root of 5. So how many square root of 5s do we have in total? Well, even what's in front, so now we have a term in front that has a variable, but that variable just happens to be the same for both a y and its exponent is also the same, both 1. So those are like terms. 18y and 8y are like terms. So we actually could put these together. So we're going to say that we have 10y root 5, and that would be our final answer. And just as a hypothetical, let's say that this was an x instead. Well, then we could say, well, we have 18y minus 8x root 5, right? So you could essentially think of it as like factoring out a square root of 5 from both terms, right? Because they share that root 5 in both of these expressions. So factoring it out leaves behind that parenthesis value, but we wouldn't be able to combine what's under here, right? Because we don't have like terms between that y and that x. So just a hypothetical there on if you saw something like that, how you could make an one additional step if you'd wanted to. And then last problem, 32H, 98H, and 50H are clearly not all the same. So we're going to simplify that. So that is root 32 root h. This time, the square root of h is the best that's going to we're going to get it. So there's no simplification like the last problem where the variable was squared. So that h is going to stay inside the square root, but we got to simplify the 32. So 2, 16, 2, 8, 2, 4, 2, and 2. So because we have a square root, we're looking for groups of 2. Because I have 2 groups of 2, I'm going to pull out 2 2's and multiply them, so I'm going to get 4. So we're going to say root 32 is equal to 4 square root of 2. Okay? So that means this thing is 4 square root of 2 times the square root of h. So going in reverse, where I can split apart radicals, I can put them back together through multiplication as long as the radicals are the same. In this case, they are. They're both the same index of 2. So both square roots, I can say this is 4 root 2h. So let's make that replacement. We're going to do the same thing with 98h. So knowing that that h is going to be under the radical, let's just take a look at 98. We have 2 and 49, 7 and 7. There's our group of 7. So this is going to be 7 root 2, and then we still have that root h tacked on. So plus 4 times 7 square root of 2h. And then lastly, you will find out that that simplification of root 50h is going to be 5 2h. Those last two terms in the initial problem had a 4 and a negative 3 as their constant coefficient. So let's take care of that multiplication. We'll clean that up. 28 root 2h minus 15 root 2h. And now we can see through simplification, all of these terms, same exact square root, and what's underneath the radical are all the same, 2h, indicating that we have like terms. So how many do we have in total? Well, we can add the first two, so we have 32 2h minus 15 2h, and then 32 minus 15, we have a total of 17 root 2h. So there's 4 examples on adding radical expressions, the procedure, what you should be looking to do, and how to combine those like terms or identify those like terms.